Welcome to this lecture on examples in probability. Today we are going to see examples of independent events and dependent events. So, independence is the main theme of the example of these examples. You must have seen Professor Arvind's lectures where he defines clearly what independence is, gives the definition, gives a lot of examples himself. So, I would like to push those examples a little bit further and get started. Okay. So, the first experiment we will see is, as usual, toss a coin, let us say 3 times. Okay. So, we toss a coin 3 times, we all know what the sample space is, I do not have to write this once again. Let me consider 2 events and then argue about their dependence and independence. Okay. So, the first event A is that first toss was heads. Let us say the second event B is that the second toss was heads. Okay. So, if you were to compute the probability, we know that the probability of A is actually 1 by 2, right. First toss was heads is 1 by 2. Similarly, probability of B is 1 by 2. So, these two are not enough to conclude about the independence of A and B. You have to compute one more probability, which is the probability of A intersect B. What is A intersect B? First toss and second toss are heads. What is the probability of A intersect B? So, you want the first and second toss to be heads. If you want, you can write it down, write down the event explicitly. You have H H T, H H H, right. So, these are the only 2 possibilities. So, probability of A intersect B is 2 by 8, which is 1 by 4. Now, what is the definition of independence? If 2 events A and B are independent, if probability of A intersect B equals probability of A times probability of B, and we can check that probability of A intersect B is 1 by 4 is actually the same as probability of A times probability of B. Okay. So, A and B are independent. That implies A and B are independent events. Okay. So, this is a very simple example. Now, from this example one tends to generalize a little bit. So, if you see what is the meaning of 2 events being independent, intuitively what it means is whether the first event happened or not does not affect the probability of the second event in any way. Okay. So, if you think about it, the way I am tossing 3 coins repeatedly, whatever happens in the first toss does not impact what is going to happen in the second toss. So, the probabilities will end up in this fashion. Okay. So, this is something important to understand from an intuitive point of view also. Okay. So, let us look at another example with throw a die 2 times, or let us say throw a die once, I am sorry. So, let us look at another example where we throw a die once. Okay. So, we know what the sample space is. You have 6 possibilities, all of them are equally likely. Okay. I am going to define 2 events here. Event A is the event 2, 4, 6. If you want in English, you can think of this event as being the even numbers, right. You get an even number. And then I am going to define another event B, which is let us say 2, 3. Okay. So, do not ask me what this event is, it is just some event I am defining, it is a valid event 2, 3. So, I am going to try and see if these 2 events are independent. Okay. So, let us do probability of A, which is 1 by 2, probability of B, which is 1 by 3, right. So, probability of A is actually the number of elements in A, which is 3, divided by the total number of possibilities 6. 3 by 6 is 1 by 2. Probability of B is 2 by 6, which is 1 by 3. So, what about A intersect B? If you look at the intersection, it is actually 2. Okay. And then what would be probability of A intersect B is actually 1 by 6. So, let us do our check. Probability of A intersect B is 1 by 6 equals probability of A times probability of B. Okay. So, in this case A and B are independent. right. It is quite easy to see that. Let us call this part A. Now, part B is another example where I am going to take something very similar for A. I will keep A as it is, then I will define an event C, which is, let us say 1 comma 5. Okay. So, this is A is the event with the I mean it is said to have happened if you got 2 or 4 or 6. C is an event, it is said to have happened if you got 1 or 5. Okay. So, that is the definition. So, if you actually compute probability of A, you have a half here, probability of C will be 1 by 3, but what happens to A intersect B? It is actually the null set, there is no intersection. So, what is the probability of A intersect B? It is actually 0. So, in your check, probability of A intersect B is 0 is actually not equal to probability of A times probability of C. Oh, I am sorry. இதை திருப்பி பண்ணுறேன் கொஞ்சம். Okay, so let us do probability of A intersect C. It turns out A intersect C is actually the null set. Okay, there is no intersection here, right? So, it is 2, 4, 6, that is 1, 5. So, probability of A intersect C is actually equal to 0. Okay, so in your check, you are going to get probability of A intersect C equals 0, which is clearly not equal to probability of A times probability of C. So, A and C are dependent. Okay. So, I think these two examples are a little bit important to illustrate one of the finer concepts in independent events. In fact, the intersection of A and B is very, very important. Okay. So, if the A and B do not intersect, then they will not be independent. In fact, if they have to intersect for independence, look at what happened in the second example. A and C did not have any intersection. Okay. So, probability of A was non-zero, probability of C was non-zero, and A intersect C became empty set. So, it means probability is 0. Okay. So, if you have no intersection, they are going to be dependent. Now, if you think about it, it makes a lot of sense. Okay. So, let us look at part B for instance. The event A is 2, 4, 6, okay, and the event C is 1 comma 5. Okay. Now, if I told you that the event A happened, right, suppose I told you the event A happened, then you know for sure that the event C did not happen. Okay. So, whether or not event A happened directly affects the probability of event C. Okay. So, that is okay, directly affects, not the, let me not say probability here, the conditional probability of event C. If C given A is going to be equal to 0 for instance. Okay. So, the fact that these two guys do not have an intersection actually leads to a lot of dependence between these two events. Okay. So, when people say independence, it is not that the sets representing the events do not intersect, it is not that at all. They have to intersect, and just intersection alone is not enough to make them independent. If you want independence, the fractions should work out, you know, the number of elements in the intersection should be exactly such that the probabilities multiply in that fashion. Okay. So, maybe I should give you one more example to illustrate what I mean by that. If you take an example here where I keep A as again 2, 4, 6, and then I keep B as let us say 1, 2, 3, or maybe yeah. So, 1, 2, 3, that is okay. Okay. So, A is 2, 4, 6, B is 1, 2, 3, and again if you do probability of A, now you get 1 by 2, probability of B you again get 1 by 2, right. So, both these events are probability 2. So, if you do A intersect B, you actually get 2, and probability of A intersect B is ending up being 1 by 6. So, now once again if you check, probability of A intersect B is 1 by 6, and it is not equal to probability of A times probability of B. So, this implies A and B are dependent events. So, here again there was an intersection between A and B, but the intersection was in a way it was too small or something like that, right. So, you are not going to get independence with this kind of intersection. So, hopefully these three examples give you an illustration of what is needed for dependence and independence. The two events have to intersect for independence to be possible, but just because they intersect, it does not mean that they will be independent. The probabilities have to work out correctly. Okay, the probability, check probability of A intersect B has to be equal to probability of A into probability of B, only then they will be independent. And also, just because the two events are disjoint, as in they do not intersect, you will, in fact disjoint events will never be independent. okay. The disjoint events will always be dependent, because whether or not event A happened tells you something about event B, right. So, that is what is very important to understand here, okay. So, independence is a little bit more subtle in this fashion, so we have to watch out when you define independence, okay. So, let me give one more example in the same spirit here. Let us say you draw a card from a pack. Okay. So, note again I am drawing only one card, okay. So, it is not two cards, I am drawing one card from one pack, okay. So, I am going to define the event A as card is a spade, card was a spade, and the event B is card was a king, okay. So, what is the probability of A? We know this is 13 by 52, which is 1 by 4. What is the probability of event B? It is actually 4 by 52, which is 1 by 13, okay. So, what is A intersect B? Card was spade king, right. Okay. So, you draw one card, one event is that the card was spade, the other event is the card was king. The question is, are these two events independent? Okay. So, we see that the event A can be written down, card was a spade, there are 13 possibilities here. Event B can be written down, card was a king, there are 4 possibilities here. Probability of A is 13 by 52, 1 by 4, that is okay. Probability of B is 4 by 52, 1 by 13, that is okay. Now, A intersect B is not a null set, okay. So, that is promising. So, card was spade king, and they could be independent, okay, but we have to verify whether the probabilities work out correctly or not. Probability of A intersect B is there is only one card here, so that is 1 by 52, and that is really equal to probability of A times probability of B. So, that implies A and B are independent, okay. So, this is a nice way of checking this. So, I am going to give you a couple of slightly non-trivial examples slowly. The next example we will see is let us say dealing a pack of cards. To 4 players, okay. So, there are 4 players, let us say player 1, player 2, player 3, player 4. This is how we play cards, is not it? I mean, you have 4 players and you deal the cards or distribute the cards to all 4 people, and each person after distribution will end up with 13 cards each, right. Okay. So, they will end up with 13 cards each, okay. So, one can think of when you can imagine how this is being dealt. So, I will assume it is a very fair way of distributing the cards, as in every possibility is equally likely in the distribution, you have shuffled the cards very much. So, that is what happens, okay. So, let me define 2 events here. A is player 1 got ace of spades. Event B is player 2 got ace of spades. Okay. So, these are the 2 events. It is I mean, many of you probably already know whether or not A and B are going to be independent. Let us look at that possibility now. It is a simple example, but before that I want to illustrate some of these tricks in probability to calculate probability. So, for instance, what is the probability of A? Let us say you want to compute the probability of A, okay. So, you have 52 cards, player 1 is equally likely to get any one of the 13 possibilities. So, you can start computing in that fashion. So, I am going to do it that way first, and then I will show you a nice little simple way to argue what the final answer has to be, and you will see it will be working out correctly, okay. So, if you look at what cards player 1 can get, there are 13 different cards out of the 52 he will get, okay. So, all of them are equally likely. So, you will have a 52 choose 13 in the denominator. Remember once again, what is my notation? This is some of you write it as 52C 13, okay. So, combinations of 13 from 52, I will also write it like this, okay. What is this? This is 52 factorial by 13 factorial times 39 factorial, okay. So, this is number of ways in which you can take 13 things out of a group of 52 things. So, now this is in the denominator, this is all the possible things he could have got. Now, in how many of these cases would he have definitely got the ace of spades? Okay, so that is one card already chosen for you, right. Ace of spades is chosen for you, there are only 12 other cards left. Out of the remaining 51, all these 12 possibilities are equally likely, okay, right. So, you will have 51 choose 12, is that okay? Okay, the ace of cards was chosen for you already, and then you have 51 choose 12. Okay. So, if you do this calculation, you will have 51 factorial by 12 factorial times 39 factorial, 13 factorial times 39 factorial by 52 factorial. Things will cancel and you will get, remember this will cancel, this will cancel. 51 factorial will cancel with 52 factorial. Remember what is 52 factorial? That is 52 into 51 into 50, so on till 1. And what is 51 factorial? It is 51 into 50 into so on till 1. So, if you write 51 factorial by 52 factorial, this 51 factorial is going to cancel and it will leave you just 52. Same way with 13 factorial and 12 factorial, it will cancel and it will only leave 13. So, 13 by 52, that is 1 by 4. Okay. So, that is the probability that the player 1 got ace of spades. Now, one might actually quickly arrive at this answer 1 by 4. If you think about the 4 events, player 1 got ace of spades, player 2 got ace of spades, player 3 got ace of spades, player 4 got ace of spades, right. There are 4 events like this and the ace of spades has to go to one of these players, right. So, all of them are together they make up the entire set of possibilities, and each of these events is going to be equally likely by some sort of a symmetry in the situation, right. So, you are distributing the cards very fair in a very fair manner. So, it should be equally likely that any player, any one player has the ace of spades. So, probability that the player 1 got ace of spades should be 1 by 4. Similarly, probability of B that the player 2 got ace of spades is also 1 by 4. Okay. Now, if you think of the intersection, what is the intersection? Player 1 got ace of spades and player 2 got ace of spades, that is actually the null set, right. There is no such event. I mean, you cannot have a distribution of the cards where both the player 1 and the player 2 has the ace of spades. Okay. So, that is not a valid pack of cards, because in the pack of cards there is only one ace of spades. So, this is actually 0. Okay. Okay. So, clearly A and B are dependent events. Okay. So, anyway, so I was just trying to give you another illustration of an example where you have to argue very carefully. So, now in many real life experiments that you want to model and real life scenarios you want to model in probability, such kind of things will happen. You will have one event and you will have another event. Using symmetry, you will have to argue that they will have to maybe be equal probability, and also you have to argue that they are disjoint in some sense. All these things you have to notice very carefully. So, hopefully this was an example that gave you the idea. Okay, so look, we are going to see one more example, which is the 5th one. Balls into bins. Okay, so let me take 3 bins for simplicity, bin 1, bin 2, bin 3. So, you remember this experiment, what happens? There are balls that you close your eyes and throw in, and it is equally likely that they will end up in each of these bins, and at the end of the day you want to count and see how many balls are in how many bins. Okay. So, let us say we throw I do not know, let us say 10 balls into 3 bins. Okay. So, I am going to define an event E1, which is bin 1 is empty. Okay. So, this is E1, and then you have the event E2, which is bin 2 is empty. Okay. So, things are going to get a little bit subtle here, you have to pay attention. Okay. So, event E1 is the event that bin 1 is empty, event E2 is the event that bin 2 is empty. Now, are these two events independent or not? Okay, that is the question that I am going to ask here. So, this actually needs a calculation. So, if you think about it, there is an E1 intersect E2. Okay, there are various possibilities under which there is a possibility under which bin 1 and bin 2 can be empty. What happens in that case? All the balls go into bin 3. Okay, so that can happen. Okay, so the two events are not disjoint, so they may be dependent or may not be dependent. May be independent or may not be independent. You have to actually calculate the probabilities and check. So, let us try and calculate probabilities here. What is the probability of E1? Okay. So, what is the probability that bin 1 is empty? Every ball when you throw, it is equally likely to go to any one of the 3 bins, okay. And I want bin 1 to be empty, which means what? Every ball should either go to bin 2 or go to bin 3, okay, right. So, every ball has 2 power 10 possibilities out of a total of 3 power 10 possibilities, okay. So, each ball could have gone to any one of the 3 bins. So, that is 3 power 10 total possibilities, out of which 2 power 10 are favorable to you. So, you have 2 power 10 divided by 3 power 10, or if you want you can write it as 2 by 3 power 10. So, now we can quickly argue that probability of E2 will actually be equal to probability of E1. Why is that? Because bin 1 and bin 2 are sort of symmetric in some sense, probability that they are both empty, each of them is empty, bin 1 is empty and bin 2 is empty should be the same, okay. So, in fact that will also be 2 by 3 power 10. So, what about E1 intersect E2? Bin 1 and bin 2 are empty, okay. Bin 1 and bin 2 are empty, okay. So, now if you do probability for this E1 intersect E2, you notice there is only one possibility for any bin ball to go to, right. You can't put it in bin 1 or you can't put it in bin 2, you should put it only in bin 3. So, there is only one possibility, maybe if you want you can call it 1 power 10, okay, divided by 3 power 10, I am sorry 3 power 10. So, that is the probability of E1 intersect E2, and you can quickly check this is not equal to probability of E1 times probability of E2. Is that right? Do you agree? So, you can see that the probability of E1 intersect E2 is 1 by 3 power 10, it is not equal to probability of E1 times probability of E2, okay. So, now there is a small calculation that I want to do here. So, supposing so this implies, let me finish it off, this implies E1 and E2 are dependent events, okay. So, let me push this example a little bit further, not necessarily in independence example, but I want to show you how to do calculations when events are dependent, okay. So, when events are independent, probability of E1 intersect E2 is probability of E1 into probability of E2, it kind of simplifies things in some fashion. But when they are dependent, some calculations become more difficult. So, for instance, since E1 and E2 are dependent, supposing I ask about E1 complement, what is E1 complement? Bin 1 is not empty. And what is E2 complement? Bin 2 is not empty, okay. Now, there is a very nice result in probability, you can think about proving it if you like. If E1 and E2 are dependent, E1 complement and E2 complement are also dependent, okay. So, you can think about it, if E1 says something about E2, clearly E1 says something about E1 complement also. So, E1 complement will also say something about E2. So, they will be dependent. If E1 and E2 are dependent, E1 complement and E2 complement will also be dependent, okay. But this E1 complement intersect E2 complement is an interesting event. What is E1 complement intersect E2 complement? Bin 1 and bin 2 are not empty, okay. So, quite often you are interested in problems like this. So, you want bin 1 and bin 2 to be not empty, and if you remember from the very early lectures, I defined this event and I kind of showed you how for this kind of events it is difficult to enumerate, okay. Bin 1 and bin 2 are not empty. So, these kind of things are slightly more complicated to enumerate. So, supposing you want to find probability of E1 complement, this is not too bad, you can find probability of E1 complement. How do you find probability of E1 complement? It is 1 minus probability of E1 and you know probability of E1. So, this is 1 minus 2 by 3 power 10, okay. In fact, this is the same as probability of E2 complement, okay. Both of these individually I can find the probability. So, how will I find the probability of this guy? E1 complement intersect E2 complement, okay. It looks a little tricky. So, it turns out one can use this very nice little trick here. So, it turns out instead of trying to find this, okay, one needs to observe this interesting little result. If you do a complement of this event using De Morgan's law, you will get E1 union E2, okay. So, this is just De Morgan's law, you saw Professor Arvind's lectures on this, okay. De Morgan's law of sets, Okay. So, E1 complement intersect E2 complement, the whole complement is actually E1 union E2. Okay. So, probability of E1 complement intersect E2 complement is 1 minus probability of E1 complement intersect E2 complement, the whole complement, right, and that is 1 minus probability of E1 union E2, because E1 union E2 is the same as this big complicated little expression with E1 union E2. So, it is easy to kind of argue this in English also, right. What is E1 complement intersect E2 complement? That is bin 1 and bin 2 are not empty. What is E1 union E2, right? What is E1 union E2? This is either bin 1 or bin 2 are empty, right. E1 is bin 1 is empty, E2 is bin 2 empty. If you say E1 union E2, it is either bin 1 or bin 2 must be empty. What is E1 complement intersect E2 complement? Bin 1 and bin 2 are not empty. So, these two clearly are complements of each other, right. So, this is the essence of the way De Morgan's law works. So, instead of finding probability of E1 complement intersect E2 complement, I will simply find probability of E1 union E2 and then do a subtraction. Now, how do you find probability of E1 union E2? So, here you can use this other nice result, probability of E1 union E2 plus probability of E1 intersect E2 is actually equal to probability of E1 plus probability of E2, right. So, now why is this nice? Because I know probability of E1, I know probability of E2, I also know the probability of E1 intersect E2. So, once I have these three probabilities, I can find the probability of E1 union E2. So, this tells you probability of E1 union E2 is probability of E1, which is 2 by 3 power 10, plus probability of E2, which is 2 by 3 power 10, minus probability of E1 intersect E2, which is 1 by 3 power 10. Okay. So, this tells you what is the probability of E1 union E2. Okay. So, what is the probability that of this other guy here, E1 complement intersect E2 complement? It is the probability that bin 1 and bin 2 are not empty, it is 1 minus this guy. Okay. So, maybe you can write it a little bit simpler, 2 times 2 by 3 power 10 minus 1 by 3 power 10. Okay. So, that is the answer. I mean, one can simplify this further if you like, but that is fine enough, we can write it down. Okay. So, this was just an example to illustrate how you can have dependent events in many real life scenarios, and how you can use this sort of a union rule for computing probabilities in a very clever way and compute all sorts of interesting events even though they are dependent. Okay. So, it is a little bit more complicated than when they are independent, but when they are dependent also hope is not lost, you can do computations with events that are dependent. Okay. So, of course, independent events are very nice, they are very easy to combine. So, you know intersecting them is very easy. A very nice illustration of this is going to come in the next example, and with that we will conclude this lecture. It is some sort of a network reliability problem. Okay. So, I am going to draw a very simple network here. Let us say you have one link here, another link here, and a third link here. Okay. So, this is let us call it point 1 and point 2. So, this is just a network, I am just drawing these nodes and connecting them with lines. You can think of them in various ways. So, for instance, these could be cities in a map, and these could be roads that connect them together. Okay. So, 1 and 2 are connected directly, or they are connected to 3, or they are connected through 4. Okay. And there might be probability of failure in any of these links or roads or whatever you want to imagine. This might be a probability, so maybe I will call equal probability. Okay. So, probability of failure of a link equals P. Okay. And in very many statistical models, you can assume that the failure of links, failure of different links are independent. Okay, now this is a very crucial assumption. Okay, so quite often when you have networks like this, it's reasonable to assume that different links are not affected by each other. So if you imagine these as roads connecting cities, maybe what happens in one road is not connected to what happens in another road, whether there is some agitation in the middle of this road which causes the traffic there to stop, or traffic on another road is stopping. They are probably independent in some sense. You can make use of this assumption in your calculation. But if you want to apply results from such a probabilistic model, you should be extremely aware of this assumption, that you are assuming that's independent. So for instance, if there was a major natural catastrophe in this entire area, okay, maybe major earthquake or something, and it's very likely that all of the roads will be cut off, right. So it can also happen. So you should be aware under which models, under which situations this kind of model of independence actually holds, and it can be violated. If it's violated, then all your inferences will go wrong. Okay, so that's very important to know about any probability model. Okay, so now one of the questions they'll ask is any particular link fails with probability p. I am interested in the event E that nodes 1 and 2 are cut off. What do I mean by cut off? They can't communicate to each other, you can't go from 1 to 2. Okay. So what is the probability that nodes 1 and 2 are disconnected in some fashion, as in you cannot start at 1 and there is no way for you to reach 2. Okay. So now you have to call these links. So let me call this L1, this is L2, this is L3, this is L4, L5, okay, right, and I will call event E1 EI as Li has failed. Okay. So now what is this event E? I can write it in an interesting fashion. You can think of it as various possibilities. So now E can occur if let us say E3 has to always occur. If E3 does not occur, right, clearly you can go from 1 to 2 always. Okay, link 3 is active, means you can go from 1 to 2 and the event E would not occur. Okay. So E3 must definitely occur, link 3 should definitely fail. Now what about the remaining links? You have to argue very carefully. Out of L1 and L2, at least one link should fail. Okay. Out of L3 and L4 and L5, at least one link should fail. Okay. So this event E, okay, if you argue it out carefully, you can write it as E3 intersect E1 or E2 intersect E4 or E5. Is that okay? I mean, or E5, I am sorry. Okay. Hopefully you saw how I did this calculation. The event E would have occurred, nodes 1 and 2 would have been cut off, E3 has to occur. Okay. So because if link 3 is active, you have a connection from 1 to 2, E3 has to occur, and between E1 and E2, I think between link 1 and link 2, at least one should fail, which is what, either link 1 or link 2 should fail. So E1 union E2. Okay, because if both are active, then clearly you have a route. Okay. Same thing happens with E4 and E5. Now remember, events involving different links are all independent, and these are all events involving different links, and I am doing an intersection of these things. So when I do probability, when I know these things are independent, I can multiply these probabilities, probability of E3 times probability of E1 union E2 times probability of E4 union E5. Is that okay? So how did I manage to do this? The independence assumption is crucial here. Independence assumption. Okay, so it's very critical. So if I did not have the independence assumptions, I cannot multiply. And the fact that I multiply tells me something about this event E. So right, in computation, when it's valid, under what situation is this valid? When you translate it into reality, you have to be aware of the assumptions you made in the model. Okay. So once you do this, it's not too bad. So this probability is just P. What is this probability? What's the probability of E1 union E2? Let me again do that carefully here. Probability of E1 union E2 is actually, again I have to use this union rule, probability of E1 plus probability of E2 minus probability of E1 intersect E2. Okay. Now what is probability of E1? That is P. What is probability of E2? That is another P. What is probability of E1 intersect E2? Remember, E1 and E2 are again independent. Okay. Whether link 1 fails or link 2 fails, it is independent. So, this becomes simply probability of E1 times probability of E2. Again we use independence here. Very crucial. Okay. So, you see here it is 2 times P minus P square. So, that is the probability of E1 intersect union E2. So, it is P times 2 P minus P squared times, what about this guy, probability of E4 union E5? You do not have to repeat the same calculation again, it has to be the same, right, it has to be the same as E1 union E2. So, you will get 2 P minus P square. So, that is the final answer for probability that nodes 1 and node 2 will be cut off. So, hopefully this illustrated to you that in your model, if you assume things are independent, any composite event, okay, can be easily decomposed in terms of individual events if they are all independent, and you can easily multiply them with each other, compute probabilities of unions, intersections, etc., in this nice fashion using both the union rule and the fact that you can multiply probabilities for independent events. Okay. So, hopefully these examples showed you various situations in which we are doing calculations. We will slowly complicate things a little bit more, we will look at more complicated examples of independence and all that as we go along in the next examples lectures. Thank you very much.